Hello 111 students. Since we have learned so much more about stoichiometry since our first map of stoichiometry, I thought I would throw together an overview video of the Map of Stoichiometry Mark II and slot in some of the new things we've learned. So here in the middle, this is the map of stoichiometry that you're already familiar with, where we have our moles to moles conversion in the middle through a chemical equation, and then we can go from moles of a substance to grams of a substance using the molar mass, and then moles to particles using Avogadro's number. Well, we've got two new sets of boxes that we can put on this thing. The first is the ability to convert between moles of a substance and a solution volume of a substance through its molarity. If you want to go from moles to volume, you will divide by the molarity, and if you want to go from volume to moles, you will multiply by the molarity. We can now also go between moles and a gas volume of a substance, and we do that through the ideal gas law. Depending on which way you're going, you just need to rearrange the ideal gas law. For a video on how to derive relationships from the ideal gas law, go ahead and check out my video that's titled Deriving Smaller Gas Laws from the Ideal Gas Law. Now here, we can go all the way from, say, a gas volume of A, cross this map of stoichiometry to a solution volume of another substance B. Let's take a look at a potential example you might need to solve on an exam. When sodium bicarbonate is mixed with acid, CO2 gas is produced, as seen in the chemical equation below. At 25 degrees Celsius and 1.01 atmospheres, how many milliliters of CO2 will result from mixing 25 milliliters of 0.150 molar sodium bicarbonate into excess hydrochloric acid? So here's our balanced chemical equation. 1 sodium bicarbonate aqueous plus 1 HCl aqueous, here's our acid, will become 1 CO2 gas plus 1 H2O liquid plus 1 unit of sodium chloride aqueous. So let's check out on our map the steps we need to go through. Well, first off, our starting point is going to be the solution volume of the sodium bicarbonate. Remember, we always want to pick starting and end points for stoichiometry problems that are in simple units. From there, we're going to use the molarity of the sodium bicarbonate to get into moles of sodium bicarbonate. Then we'll use the chemical equation to convert that to moles of carbon dioxide. And finally, we'll use the ideal gas law to get to our final answer of the gas volume of that carbon dioxide. Let's see it in action. So we're going to begin by doing the stoichiometry to get from our volume of sodium bicarbonate to our moles of CO2. And that looks a little something like this. 25.00 milliliters sodium bicarbonate. In our next term, 1,000 milliliters becomes 1 liter. Then 1 liter becomes 0.150 moles of sodium bicarbonate. We pull the mole-to-mole conversion from our balanced chemical equation, which is 1 mole sodium bicarbonate becomes 1 mole carbon dioxide. If we crunch our numbers, we get that we have made 3.75 times 10 to the minus third moles of CO2. Well, now it's time for our ideal gas law. PV equals nRT. Whenever you're using this equation or others like it, it's really helpful to make a table of variables first. Pulling from our problem, we know that our pressure is 1.01 atmospheres. The volume is the thing we're trying to solve for. We just calculated that our N is 3.75 times 10 to the minus third moles. Looking down at temperature, temperature for the gas law always has to be given in Kelvin. So we're going to add 273 to our Celsius temperature of 25 to get 298 Kelvin. And because of the units on these other variables, we're going to use the R value of 0.08206 because it possesses the units needed to cancel out all the others. So now that we know we need to solve for V, we're going to first rearrange the ideal gas law so that we are automatically solving for V. V equals nRT over P. Now all we need to do is plug in our numbers and crunch. So if we plug in the appropriate values, we're going to get a final answer here of 0.0908 liters of carbon dioxide. But we're not quite done yet. Remember, the problem asked us for milliliters of CO2. So we need to do a quick unit conversion first. Our 0.0908 liters of CO2, 1 liter will become 1,000 milliliters, so our final answer is 90.8 milliliters of CO2. So this was the Map of Stoichiometry Mark II. We simply added on the ability to do stoichiometry in solutions and stoichiometry with gases. Just you wait for next semester when the Map Mark III is going to add some things to do with redox and electrochemistry. I will see you guys in class.